Good morning, everyone. My name is Phil Miller. I'm a fourth-year PhD student in the Parallel Programming Lab, and I'm one of the large team of people that worked on our submission to the HPC Challenge that was presented and awarded at Supercomputing 2011 back in November. So the HPC Challenge submission is based on a collection or suite of benchmarks. Some of them are very recognizable to many people. There's dense LU factorization. That's the standard LinPack numbers that are used to produce the top 500 list. There are also two other standard benchmarks that come as part of the suite, FFT and random access, which I'll explain in some detail as we go through the talk. And then they also offer the opportunity for submitters to the challenge or entrants in the challenge to offer some benchmarks of their own that they think exhibit the unique characteristics of the system that they're entering. So just to give you a little bit of a spoiler almost of the results that we saw in our submission. We ran from a range of 8,000 to 64,000 processors for the various benchmarks, and you can see the various performance numbers that we got out of this. So the reason that LU is so far behind some of these others is that LU is a weak scaling benchmark, the way that it's specified in the HPC Challenge. So that 8K run takes 4 hours or 6 hours, something like that. And as you scale up, that increases substantially. So you can waste a lot of SUs doing these submissions. The same sort of problem that the people actually making runs for the top 500 run into. So we stopped at 8K when we saw, They don't have an SU problem, except for other people want to burn their SUs, and those runs prevent them. So we have an SU problem there. So for the Argonne folks, if you'd like to donate, the entirety of Intrepid for a week, we could do some larger runs. But yeah. So the other aspect of the HPC Challenge Class 2 submission, which is the programming models competition, is that they look at the so-called elegance of the submitted code, and this is judged primarily in terms of lines of code. And so you can see, the range of code sizes in what we submitted. So LU took, about 1,650 lines. For comparison, HPL, the standard reference implementation, is about 12,000 lines of code. Another comparable implementation in UPC was about 4,000. So we think we placed pretty well. We didn't quite catch up to Parallel MATLAB, which was submitted a couple of years ago, whose implementation was the single line x equals a/b. But Cleve Moeller was apparently very proud of this. But yeah, that hasn't been repeated since then. So the other benchmarks are all pretty tiny. Well, mostly pretty tiny. And I'll go into some more detail about these benchmarks over the course of the talk. So just to keep in mind, when you're looking at all of these numbers, a lot of things come for free in the Charm++ system, including load balancing for the benchmarks that have dynamic load imbalance, fault tolerance, again, for benchmarks that aren't running at the limits of machine capacity or where you just don't care what fails. Yes, Ron? I mean, they don't say that explicitly, but that seems to be what it came down to, was that the shortest code wins on elegance. And also, we, again, just by virtue of the Charm++ programming model, get automatic overlap of communication, computation, of different phases of computation where they don't directly depend on each other. We get composition of multiple parallel activities at once, and we get machine portability with minimal tuning. So let's first focus on the LU implementation, which was kind of the biggest part of this effort and generally gets the most focus in the discussions of the HPC Challenge. So one important aspect of our LU implementation, in contrast to other submissions and to standalone benchmark implementations like HPL, is that we implemented our LU as a composable library. So it is actually possible for someone who needs LU factorization, linear system solver, in their Charm++ program to pick up the code we wrote and plug it in directly and call into it. And if their code has other things that it's going to be doing at the same time as this linear system solve, it can keep running those. It doesn't need to transfer control into the LU module and then transfer control back. It can instead interleave execution completely seamlessly. So another unique aspect of our implementation is that it is block-centric. Most algorithms, or most implementations, focus on a processor-centric decomposition where the processor owns some collection of blocks and it tries to operate on everything it owns all at once. And this presents some trade-offs. There's slightly better sequential efficiency to be had if you treat all of the blocks on a processor as a unitary entity. But at the same time, it also limits certain flexibility, and it forces a certain way of thinking about the implementation, which is not necessarily desirable. So what this also means for us is that the implementation of the mathematical part of the algorithm, that actually describes an LU decomposition, is completely agnostic to processor-level concerns, and I'll detail some of what those are in just a moment. Okay. And the last interesting point that builds on this whole agnostic from processor-level concerns is that we actually have a very strong separation of concerns in the code that we've implemented. So what that means is that the domain specialist, your numerical analyst, your applied mathematician, whatever, can focus on the LU implementation. And the system specialist, the people working in our lab and people with the deep architecture knowledge, the deep parallel computing knowledge, can focus on tuning and resource management and all of those peripheral concerns that the person writing the numerical algorithm shouldn't have to trouble themselves with too much. So just to illustrate this point, we've separated out the contents of the code into a few different areas. So there's the factorization, which is the algorithm itself. There's the memory-aware scheduling, which I'll talk about in a little bit more detail. And there's the mapping, which we heard about in Jonathan's talk yesterday. And what we could see is that based on the commit history in our version control system, a large fraction of commits made against our benchmark implementation only touched one of these areas. And and obviously with some assumptions that we're not just artificially committing things separately, because these numbers were generated after the fact, so we weren't planning for them. This was just an ad hoc experiment. What this shows is that essentially only to make changes to a particular piece of the benchmark, one only had to touch the piece that was actually relevant to what they were working on. It didn't require changes strung throughout the entire code base. In contrast, in HPL, where we looked at doing our mapping variations that we discussed in Jonathan's talk yesterday, the same changes would have required changing a huge fraction of the code because the mapping from blocks to processors is inherent in who is an MPI call communicating with. And that makes it much more difficult to do these sorts of experiments that we showed. So just to remind you about how this all works, we did a square block decomposition of the LU factorization. And so at any given time, there's a column of blocks that are the active panel, which are doing very fine-grained work interleaved with very fine-grained collective communication. And then there's the contents of those blocks are transmitted to the rightward blocks from that. There's some triangular solves in the first row, and then there's matrix multiplies in the remainder of the matrix to update it before the next step of the factorization continues. And in those active panel blocks, what we have going on is a column-by-column computation. So it's very fine-grained, and it's also very latency sensitive. And it's tightly coupled. So if anything interrupts one processor that's working in that area, that means that the entire panel factorization is going to be delayed by that. So the way we addressed this in our implementation was we actually took a small step back from the fully asynchronous, opportunistic execution model, and instead did a little bit of explicit scheduling on each processor. And the way we did this was we were able to check when all of the blocks that were going to be in the next active panel on a given processor were ready to actually execute that. And at that point, we shut off execution of the bulk work, the trailing update, matrix multiplies, and the triangular solves, which could completely swamp the fine-grained execution of the active panel computation. And so what this produces is a kind of a banded execution trace where you have these big, long blocks, and this is not to scale, this is just an illustration, but you have these big, long blocks that are the matrix multiplies, and triangular solves, and then every so often, a group of processors that own active panel blocks will switch into this mode where you have these very fine-grained work units. And what they're doing in that is they're contributing to a reduction to find the pivot row, that's the largest element in the given column, and swapping that onto the diagonal. And then they're computing a rank 1 update in the remainder of each of those active panel blocks so that they can then go looking for the next pivot row. And this actually shows an optimization that we tested out for optimizing this even a little bit further, which is that as the reduction tree to identify the pivot row passes through the relevant processors, we hold even that rank 1 update, which is coarse-grained compared to the pivot identification and reduction, until the reduction passes through, so that we don't risk delaying even that reduction. And we found that this provides a small benefit, much easier to measure on BlueGeneP than it was on Cray, just because of the relative predictability from run to run on those. And we also found that as one strong scales, this benefit becomes somewhat more noticeable. So we suspect that if we really push that much further, there might be something interesting to see there. So other capabilities of our LU implementation, you heard all about the flexible data placement from Jonathan's talk yesterday. That collection of blocks in the matrix is a 2D char array. We can map them onto processors pretty much arbitrarily, up to the limits of the memory capacity, which is generally the limiting factor in LU benchmark runs. The other neat feature.
Can you comment on how many chunks, how many jars you had per processor?
So in general, it was a few hundred. Yeah, it would be about 2 megabytes per block, so 2 megabytes per jar, occupying something like a gigabyte of memory per core. So yeah, about 500 jars per core in the XT5 runs. So the other interesting capability that we have in our implementation is what we call memory-constrained adaptive look-ahead. So in HPL, there's a certain amount of memory that's statically set to be available at the beginning of each run for looking ahead in the matrix factorization. So how many blocks ahead of the trailing updates the active panel factorization is allowed to run. And the reason this is necessary is because the block data that's used for doing the calculations in HPL is sent through tightly scheduled broadcasts at particular times, and any data that's broadcast is only going to be transmitted once. So a processor that is receiving that broadcast has to hang on to the result of it until it's actually done doing computations using that data. What we've done instead is we implemented a scheme whereby every processor keeps track of how much memory it has available for incoming block data at any given time, and it keeps a queue of what blocks it's going to need to do further calculations. And as it works through that queue, it sends requests to the processor that owns any given input block that it needs. And those processors periodically multicast to whoever has made a request to them. So to the set of processors that have requested any given block. And what this does is that it gives us completely dynamic memory usage control while still maintaining very high utilization over the entire system. So normally what you'd have is you do a broadcast from here, and you do a broadcast from here in a process row or a process column, and we've replaced those with explicit, we've replaced those with broadcasts saying this data is ready now, and then from there, that activates blocks to make the requests, but the actual transmission of data is held until the per processor memory scheduler is ready to find space for a given incoming block. So in terms of performance, you've seen these numbers yesterday, but just to refresh your memory. So we did weak scaling runs on the XT5 rendition of Jaguar back a year and a half ago now. And we got a pretty steady 65 to 67% of peak, so pretty much perfect weak scaling from 112, 128 cores all the way out to 8K cores. And we also did some runs on BlueGene-P. We didn't want to do weak scaling just because it did cost us SUs. And BGP cores are not ridiculously fast, so it was going to take a while. But instead we did strong scaling runs of LU, which is generally considered a fairly hard thing to do efficiently. And what we found was that from 256 cores out to 2K, we got pretty much a constant efficiency. And of course that's not going to be perfect scaling, because as you strong scale LU, the load imbalance increases and you get more and more idle time at the end of a run. And it's just starting to fall off as we go up to 4K on there. So, but overall, these were our results for LU. If people have questions about that, I can pause and take them here. So as I'm now going to move on to some of the other benchmarks in the HPC Challenge suite. So the next benchmark in the HPC Challenge suite that we implemented is the standard FFT benchmark. And we implemented this with a fairly standard 1D char array decomposition. And the way this worked, out was this is the entire control flow for each char. Very simple thing. So we did a transpose-based algorithm, and it just does a loop of 3 rounds of transposes and local FFTs. And so it sends transposes, waits to receive the number of transpose operations that you expect, transpose messages that you expect to receive. That's effectively an all-to-all. And you'll see that it's looking for P messages, which seems like a very inefficient all-to-all, but that's not in fact what's happening under the covers. And then, it executes the sequential FFT, and if it needs to, it calculates and multiplies the twiddle factors. So the way we get around what looks like a very inefficient point-to-point all-to-all implementation is through this library that's called the MeshStreamer. So what this provides is an asynchronous, non-blocking, topology-aware, combining streaming all-to-all implementation. So that's quite a mouthful, but the underlying principle is pretty straightforward. Essentially, every object is going to generate a bunch of messages directed at a particular destination char array index, which lives on some processor. And a processor-level entity, implemented as a group in Charm++, combines these messages and buffers them to destinations along each dimension of a mesh, or when we're running on BlueGene-P, specifically along the physical torus. And in each dimension, it batches up messages to a particular plane or to a particular column, and it delivers those to a processor on that section of the torus. And then the messages are reshuffled and combined and forwarded along successive dimensions until they reach their ultimate destination. So we can see we go from the plane to the row to the column where a destination processor actually lives with that. So what this provides us is much improved scalability in the FFT implementation. So the blue line down here is our performance without the mesh streaming library. And we can see that it reaches 2K, and then it basically flatlines in performance. In contrast, when we run the same code, the same client code, the same FFT that I showed before, but using MeshStreamer to actually send the transpose all-to-all, we get the red line, which, after the initial variability, pretty much straightens out to, perfect scaling. We see that the sequential efficiency is still, off from the serial FFT limit, but that's, at approximately the same place as other implementations of parallel FFT, that when you actually have to move data across the network, you can't come close to the bandwidth of local memory. So the third standard benchmark from the HPC Challenge suite is what's called random access. And what this consists of is every processor builds a big table in memory and generates a stream of pseudo-random numbers. And that stream of pseudo-random numbers is used as a series of targets for randomly updating some element in that global memory table. And this is very much a test of small message performance and overall injection bandwidth of a parallel system. The benefits of Charm++ in this implementation included the quiescence detection mechanisms that efficiently let us know when all of the updates across the entire system were finished, and automatic detection of the network topology to efficiently communicate these update messages. And for performance, we used the same MeshStreamer all-to-all implementation that, even though it's not strictly an all-to-all in the MPI collective sense, it's a many-to-many communication pattern with the same lack of obvious structure that the MeshStreamer is good at supporting. And so this gives us, effectively much larger messages because they get batched up and bundled before they go out. And so the performance of this, again, scaled very well. So the performance is measured in giga updates per second for some large fraction of memory being filled up with this random data. So we scaled from 128 cores to 64,000 cores. This blue line is perfect scaling. The red line is the performance we actually achieved. And what we saw was on the order of, is that 50% efficiency, I think? If that top is 40. No, 50 to 60% parallel efficiency, going from 128 all the way up to 64,000 processors. So we expect that this could actually probably compete even with the Class 1 submissions for random update.
In fact, the Class 1 machine awards were done in that time. I think the machine was it 80 something or 100 something cuts? Well,
yeah. If you multiply this out, to run on the full machine, we probably match the Class 1 entries. So
we probably match the Class 1 entries, but they don't use the library approach. They use, they'll use things like, instead of division, bit shifting and such. Actually, also the benchmark is surprisingly dependent on computation performance.
Okay. So, in addition to the required benchmarks from the HPC Challenge suite, we also implemented a couple.
So we have to
Oh, okay. I'll rush through this then.
and that's at the half an hour mark. So
Okay. So we also implemented a couple of optional benchmarks, molecular dynamics and Barnes-Hutt, n-body codes, both based on applications with which we have deep experience and, some of our experts here in the audience. So the challenges with these were load balancing and dynamic communication structure, and they also express non-trivial parallel control flow, which is a strong challenge for other parallel programming models. So the MD code mimics NAMD in its force calculation. It's similar to mini-MD from the Mantivo suite, but it's also about a quarter of the size of mini-MD. So and it uses NAMD's decomposition strategies, one-away patch compute or two-away patch compute decomposition. So the performance, once we added load balancing, we did some benchmarks on Hopper. We saw pretty much perfect scaling from 200 some cores up to 16,000. On Intrepid, again, up to several thousand cores. We got very good scaling, and it's only just starting to tail off at 32,000, where we're at the strong scaling limit of the code, because we only have a handful of atoms per core at that point. Another important aspect of this, in contrast to other implementations, is that we can run with good performance on any number of processors and actually get speed up with each incremental addition of processors, which is unusual for benchmark codes in general and even for many production applications. So in Barnes Hut, the dynamic or adaptive overlap of communication and computation was a key feature from CHARM because it involves both local work and computation and requests for remote data that are also necessary for local updates. So we could make remote requests and then start running local computation until the remote data arrived. The load balancing infrastructure in CHARM++ was also helpful because it does the instrumentation outside the application's own logic and can automatically reposition chars for optimal communication efficiency and load balance. So the scaling of that was also very good, and this is with what's called a Plummer distribution of particles, which is highly non-uniform and is ostensibly very challenging for efficient parallel implementation. So you can see the distribution of distances from the system center of mass as shown in the graph here. So it's all over the map. So with that, I'll thank you and take any questions. Yeah. Question is, what operating system features would we want for the memory-constrained adaptive look-ahead? I think what we would most want there, and this would also require support in the runtime, is not actually an operating system feature so much as a communication stack feature of being able to send a single message from disjoint buffers, say, an envelope and a payload buffer, so that we could and similarly to receive messages in perhaps a split-phase fashion, where you get the envelope presented to you, and then you can tell the communication stack where to actually put the bulk data, either by allocating it explicitly at that point, or by having, a table where you can look up where that data is going to be placed, so that we could avoid doing allocation in the message receive path. This is something that would require runtime work as well. I think Lappy provided something in that vein. And maybe Pandy does not. Okay, I didn't know that. Okay. Okay. So, yeah.
Okay, Ashram.
Yeah. So you mentioned the usefulness of having
Yeah, go ahead.
So you mentioned the benefits of having constrained look-ahead in the weak scaling case for LU. Did you see a need for similar techniques for constrained scheduling when you are doing in a strong scaling regime where memory is not an issue?
So in the strong scaling regime where memory is not an issue, we essentially simply don't have a look-ahead limit because the scheduler will queue up requests for the entire run essentially before it's even started. It can see what blocks it has, it can compute what blocks it's going to need, and just request them all eagerly.
In other words, it will automatically adapt to that situation.
Yes. You tell it how much memory is available, it compares that to how much memory is occupied by its own data, and it emits requests to fill up the rest.
But did you still have to constrain the schedules for the pivoting part?
Oh, so the constraint schedule for the pivoting, yes, I believe that was still desirable, because otherwise, so the relative scale was, an active panel factorization was maybe 40 or 50 dgems, I think. So adding, executing one dgem in the middle of it would mean that you've, increased the time on that critical path by, a couple percent. And if that happens a few times across all of the processors, suddenly, it's taking 30, 40% longer than it should. And processors are running out of work.
Okay, I think we should stop here. Thank you.
Okay.